Good morning, afternoon, or evening. How y'all doing today? Welcome back to Mr. Morrow's Honors Geometry class. Today we're going to be talking about areas of regular polygons, okay? Please remember polygon is a figure made up of three or more straight sides, okay? Triangles, squares, rectangle, quadrilaterals, etc. Octagons, pentagons. Do you remember what regular means, by the way, guys? Every angle and every side, they are all equal. Very good. Let's look at some old formulas that are going to be very important for this chapter. Does anyone remember the total interior angle sum measure of any polygon? How do I find the total interior angle sum? That's exactly correct. That's n minus 2. Oh, this. Hold on, guys. Give me 1 second. Okay, sorry about that, guys. So anyways, the total interior angle sum measure of any polygon is n minus 2 times 180, where n is the number of sides. How would I find the individual angle of any regular polygon then? Yes, sir. That's exactly correct, my friend. N minus 2 times 180 divided by n, where again, n is the number of sides. And this one was not too long ago. Who can tell me or remember how to find the central angle of any regular polygon? Yes, sir. Excellent, my brother. Excellent. 360 over n, where again, n is the number of sides. This is going to be very, very useful and handy. You've got to know this backwards and forwards. Just like I told you guys, you need to know the 30, 60, 90 and the 45, 45, 90. Well, you also need to know this. You're going to need to know both in this section, my friends, both. You're going to have to know the 30, 60, 90 triangles backwards and forwards, and the 45, 45, 90 triangle backwards and forwards, and these equations here. Okay, now let's talk about two different terms. One of them, the radius, and the other what's called an apothem, okay? A radius of a regular polygon is a segment joining the center to any vertex. Let me explain what this means, though. When you have a polygon inscribed in a circle, okay, the distance from the center to the vertex of that inscribed polygon is also mirroring the radius of that circle, correct? Yes. Right, guys? So all of these are radii, right? And they are congruent, correct? Okay, since it's a regular polygon, this is going to make equal triangles, correct? Okay, keep that in mind, okay? The radii here are all equal. So when you cut these up, they're going to be equal. No, they're not necessarily equilateral triangles, but they're just all equal triangles. No, who is to say that the radii is the same side as the side? You can't say that. Well, no. These two guys will be congruent, but these guys may not be congruent. Equilaterals where all sides are equal. Now, they're all going to be isosceles, and they're all going to be equal isosceles, but not necessarily will they be equilateral. Can they? Yes. But what happens here is I'm breaking these up into equal triangles, period. Yes, sir, my brother.
Angles from the center, would those be congruent?
The angles from the center. This right here?
Yeah. They are.
Absolutely.
Right there, you see just a circle.
I understand. They're all equal triangles, my man. But they're not equilaterals. Equilaterals are triangles that have 60 degrees each angle, and they're all equal sides. No. I want to show you. Just because this is congruent to this, does that mean that it's congruent to this side? No, it's not. No. This could be 10, my man, and this could be 20. Then that's a 10, 10, and 20. That's an isosceles triangle, but they're not equilateral. This central angle has to be 60. in order for it to be. So in this particular case, 1, 2, 3, 4, 5, 6, in this particular case, they will be equilateral. In this case, because the central angle is 60. In this particular example, though, I don't want you to think that it's always going to be equilateral triangles. They are going to be isosceles. And remember, just because it looks like it does not mean it is. All right. Now, an apothem. Yes, sir.
If you proved all chords congruent, then those would all be equilateral triangles. What?
Okay, no. Okay, no. All of these chords are congruent, guys. Of course, these chords are congruent because it's a regular polygon. That does not necessarily make these equilateral triangles, because the chords could be 20, but the radii could be 10. So it could potentially be equilaterals, yes. Is it a given that they're always equilaterals? No. In this particular case, they are, because the central angle is 60. Okay, now, let us continue. An apothem of a regular polygon is a segment joining the center to the midpoint of any side. Now, this is what we're going to be working with here. This is another example of a radii. However, this time when a circle is inscribed inside of a polygon, the radii is called an apothem. Notice that now, if I come from the center and I go to my vertex, is that the radii of the circle? No. The apothem is the radii of a circle that is inscribed inside of a polygon. Please be aware of that. And there's a lot of things that are going on with this apothem. This apothem here, okay, first of all, is perpendicular to the side of the polygon that it intersects with. Next, as you can see, it bisects the side of the polygon that it intersects. And also what the apothem does, it's an angle bisector to the central angle. So the apothem bisects the central angle, bisects the opposite side of the central angle, or the side of the polygon that it intersects, and it bisects it, and it's also perpendicular. You guys with me so far? Okay. So, if I gave you this here, O would just be called the center. Very good. Now, what would OA be here in this case? The radius in this case. What would OM be in this case? The apothem. Why do I tell you this? Well, sometimes the apothem is the radius. Sometimes the apothem is separate from the radius. And you have to be able to know which is which. When the polygon is inscribed inside of a circle, as you see here, the radius is different than the apothem. When the circle is inscribed in a polygon, though, as you saw in the above example, the apothem is the same as the circle. Okay, you with me here so far, guys? All right, because now it's gonna get fun. Things again that you have to know about the apothems and the radii. All apothems of a regular polygon are congruent. Period. Whether it's a polygon inscribed in a circle or a polygon circumscribed about a circle, all apothems of a regular polygon are congruent. Only regular polygons have apothems, by the way. Only regular polygons have apothems. What we're going to learn today is area of regular polygons. This does not work for non-regular polygons. An apothem is a radius of a circle inscribed in a polygon. We talked about that already as well. An apothem is a perpendicular bisector of any of the sides of the polygon. We talked about that as well. And a radius of a regular polygon bisects the angle of the polygon. And I think I messed up. It should be, because it could be both the radius and or, so we're going to put here, and or the apothem of a regular polygon bisects, and not just an angle, but the central angle of the polygon. Okay, that makes more sense. All right. These are things you must commit to memory. But not just memory, but understanding. The apothem bisects the central angle. The apothem is a perpendicular bisector to the side of the polygon from which it was created. Very, very important, guys. This is not just piecemeal here. We're going to have to apply this. Everyone with me so far? Okay. Yes, sir.
The only one that applies to the radius is 3 and 5. The other three are talking about the apothem.
Come again?
Like it's only 3 and 5 that's talking about the radii. The other
Well, no, the radii can be the apothem. Aren't all radii congruent as well?
Good question.
Okay. Okay, let's continue. Now, the area of an equilateral triangle. Okay, the good news here, there's two different ways to solve this, and luckily, I'm going to teach you both. I'm going to teach you the formula of an equilateral triangle, which, believe it or not, is sometimes difficult to understand. It's sometimes, not understand, I should rephrase that, sometimes difficult to memorize. The formula for any equilateral triangle, remember an equilateral triangle is a regular polygon, is s squared, the side squared, divided by 4 times the square root of 3, where s is the side. Okay? It's literally that simple. If you can memorize that, well, then giddy up. It's awesome. For example, if I say find the area of this equilateral triangle. Yes, sir. That's exactly correct, my brother. 12 squared is 144 divided by 4 times the square root of 3. That's going to be 36, correct? So my area would equal 36 square root of 3 units squared. Okay? That's simple. However, it's yet just another formula to learn. And sometimes, you know, the brain gets a little confused. So, because it's yet another formula to learn, and I want to be honest with you, sometimes I forget it. So when I forget it, I just use the alternate method. The good news about the alternate method, this alternate procedure is how you find the area of any regular polygon, period. What is the method? Okay. Number 1, find the central angle. Okay? Find the central angle. What is the central angle? Well, you're going to go ahead and estimate a center here, and you're going to make a central angle. Okay? Formula for central angle is 360 divided by n. So in this particular case, my central angle will equal 120 degrees. So this whole thing here is 120. Okay? First thing you're going to do, find central angle. Number 2, you're going to create and calculate an apothem. All right? This is easy. Drop down an altitude. That's creating your apothem here, right? You with me here, guys? The apothem is a perpendicular bisector, correct? So that means that it breaks this side in half. If the whole side was 12, that means that this side is going to be 6, correct? You with me here, my brothers? Okay. The apothem also is an angle bisector. So that means that this is now a 60, correct? Okay, now here comes the old knowledge. I gotta find the apothem. This little guy right here, A. If 6 is the side across the 60, what is the small side across the 30? Yes, sir. No. Whenever the side across the 60 is a whole number, like here, guys, you're going to multiply it by square root of 3 over 3. It's the same thing as dividing by square root of 3 and then rationalizing, but I taught you to do that as a trick. So that's going to equal 2 square root of 3. That's my apothem. Okay? You with me here? Yes, sir.
Can you just drop an altitude from the top, like a 30, 60, 90 triangle, and then start from there?
You could do that as well, but like I said, I'm trying to teach you this so that now you're prepared for the next polygon. But thank you. What he asked was, can't I just drop a whole altitude from here and then find the same thing and then do base times height divided by 2? The answer is yes. But I'm trying to think a little bit more globally. Step 3. Find the area of the new triangle and multiply it by 3. Okay. So here in this particular case, this is a triangle that I have here. And my base is 12 times my height is 2 square root of 3 divided by 2. So this is 12 square root of 3. But that's for that one triangle that I have here. But don't I have 2 other equal triangles? So multiply that bad boy times 3, and you get 36 square root of 3. Okay? Now, if you focus on this, you may catch something. You may realize that you can find the regular polygon here a little bit even easier yet. Once you find your apothem, what's the perimeter of this triangle, guys? 36. Very good. So area will equal apothem times perimeter times 1/2, actually. Okay? Yes, sir. Yes, sir. No, you shouldn't have. No, you shouldn't have gotten a different answer. Well, wait, no. If that's gonna be 30, so the apothem will be 6 square root of 3, right? So 12 times 6 square root of 3 divided by 2. That's 36 square root of 3, kid. Bam. Okay? All right. Okay, now let's continue. So the area of any regular polygon is 1/2 the apothem times the perimeter. Wait. Okay. So we've got 1/2 the apothem times the perimeter. That's a lot easier than learning side squared divided by 4 times square root of 3, in my opinion. And again, the procedure, almost identical to what we just learned, except we're not going to multiply the area of the triangle by the number of triangles inside the figure anymore. We're actually going to apply this formula right here. So what's the procedure again? Number 1, find the central angle. And again, you make a central angle by literally making a little triangle. And you have 1, 2, 3, 4, 5. This is a hexagon. 36 divided by 6 is 60. So 60 is my central angle. Number 2, create and calculate the apothem. So I'm going to drop down my apothem altitude, which is the perpendicular bisector. So I'm going to cut this guy into a 4 and a 4. This is the apothem I'm looking for. I also am going to bisect this angle. So now that's 30. So if the side across the 30 is 4, what's my apothem, which is the side across the 60? Very good. My apothem now will be 4 square root of 3. Now it's Mickey Mouse time. Find the area of the new triangle and multiply by n number of sides. No, bad. I shouldn't have said that. I should have said find area by using the formula. Now, you could do this. It's not that this step 3 is wrong, but the whole point of the formula is to shorten that up. Why would you want to find the area of the triangle and then multiply this in this case by 6? That's just too much work. Use the formula. Area equals 1/2 of apothem, which is 4 radical 3, times the perimeter, which is 8 times 6, which is 48. So divide 48 by 2, that's 24. 24 times 4 is 80, and 16, 96. Square root of 3 units squared. And that's how you find it for any polygon. Now, it's very pretty when you have nice, beautiful central angles like 60 and 120, where you're going to get a 30, 60, 90. However, what happens when you get an odd polygon? You're going to have to use, no, Pythagorean theorem has nothing to do with the angles. You're going to have to use trig. Sokotoa. Okay? For example, why don't we check this out? A regular polygon has a perimeter of 40 and an apothem of 5. Find the polygon's area. Well, in this case, this should be a joke, right? A regular polygon is 1/2 of apothem times perimeter. So in this case, I gave you everything. Area equals 1/2 of apothem times perimeter. So that equals 100 square units. Every once in a while, they'll give you the apothem and the perimeter, and that's just bing, bang, boom. You plug it in, and you're done. Nice and easy. Nice and easy. Okay? So that should be cake if I give that to you. Example 2. An equilateral triangle has a side of 10 centimeters long. Find the triangle's area. If you can remember the formula, darn it, it's a lot easier that way. What is it, my man? Side squared over 4 times square root of 3. So in this case, this would be 100 divided by 4 square root of 3, which would be 25 square root of 3 units. Oh, no. In this case, it's centimeters. So centimeters squared. Now, if you did not remember that, don't stress. You have a triangle here. All sides are 10. Drop an apothem. You know the central angle is 120, so that's a 60. This side here is a 5. I want my apothem. If my side here is a 5, what's the side across the 30? When the side across the 60 is a whole number, you multiply that by square root of 3 over 3 to find the small side. So that's my apothem. So my area would equal perimeter, which is 30, times apothem, which is 5, radical 3 over 3, times 1/2. So 3, that goes to 10, divide by 2, that's 5. So that would be, again, 25 square root of 3 centimeters squared. So I don't want you to get scared if you forget the area of an equilateral triangle. It is faster, I'm not going to lie. But you have an out. You have 2 ways here. Okay? Everyone with me here? Okay? Example 3, a circle with a radius of 6 is inscribed in an equilateral triangle. Find the area of the triangle. Okay, the circle is inscribed inside an equilateral triangle. So I have an equilateral triangle, and the circle here is inscribed inside of it. Has a radius of 6. So my radius of 6 in this case, wouldn't that be the apothem? So that's my radius of 6. I want you to find the area. Now in this case, not so much luck. You can't reverse the equilateral triangle formula because you don't know what the side is. However, what's the central angle of this triangle here? 120. Doesn't the apothem cut it into half? So wouldn't this be 60? And this is 30, correct? So what's the side across the 60 here? No, it'd be 6 square root of 3. So what's the whole side length? 12 square root of 3. Now I can find my formula, use my formula. Equals side squared, which is 12 square root of 3 squared divided by 4 times square root of 3. 12 squared is 144. 144 times 3 here. 144 times 3 is not going to be 300. 144 times 3 is 432. Okay? 432 divided by 4 is 108 square root of 3 units squared. If you didn't want to remember that, or you don't remember that, you could use area equals apothem, which is 6, times perimeter, which is 36 square root of 3, times 1/2. That goes to 3, and again, you're going to have 108 square root of 3. You have a question, my brother?
I was going to say that would probably be the easier one to do. Is that one.
Yeah, you can go either way here. Yes, sir. Yes, sir, you can. That's why I like to give options for the equilateral triangles especially. Okay? Sir? Okay. So, let us continue, gentlemen. May I continue? Okay? Now, find the area of a regular hexagon with sides 10 units long. Okay? So I have a hexagon. Hexagons are nice and easy because they produce very pretty central angles. Make a central angle here. You know the central angle is going to equal 360 divided by 6 is 60. So the sides are 10. So when I drop my apothem, I cut the sides into 5 and 5. My angle gets bisected. That's 30. So what's my apothem here across the 60? 5 square root of 3. So now it's Mickey Mouse time. Area equals 1/2 of the apothem times the perimeter. 6 times 10 is 60. So that's 30. So we have 150 square root of 3 units squared. Gotta admit, it's pretty simple. Okay? Pretty simple. Yes, sir, my brother. Okay, in this case, these guys are not radii. It depends.
Oh, yeah, sorry.
It depends. It could be, if I make my circle around here, then they are radii. Yes, sir. If I make my circle here, then they are not radii. Either way, this is the apothem. And to answer your question, either way, these two legs are congruent.
No, but how do you know that it's 60 when you draw it? Is that just stated?
Central angle is 360 divided by 6. So my central angle here is 60. When I drop an apothem, sir, it bisects it, so that's 30, and it creates a 90. 30 plus 90 is 120. So my only other option is to have 60 degrees here. Thank you so much. Excellent question. Okay, and now the fun part. Find the area of the regular pentagon this time. Okay, we could say bye-bye to pretty little angles. This is where we have to use trig. Okay? Whoa. Okay? Now, please listen, guys. Please pay attention. First of all, the sides are 16. Okay, that's great. There's not that much to worry about, though. You're still going to find a central angle. But in this case, when you take 360 and you divide it by 5, you get 72, bro. Okay? So my central angle is 72. So when I drop my apothem, I'm still creating a perpendicular bisector. I still bisect these sides. That's 8. But this time, this is half of 72, which is 36 degrees. That's not a 30, 60, 90 triangle, is it? But I still have to find my apothem, don't I? So remember, guys. So, ka, toa. Okay? What sides am I using? What trig function am I using here? Tangent. So the tangent of 36 degrees equals opposite over my adjacent, which happens to be my apothem. Multiply both sides by a, and then divide by tangent of 36. So my apothem will equal 8 over the tangent of 36 degrees. Please remember to make sure your calculators are in degrees here. 8 divided by tangent of 36. My apothem will equal 11.01. Once I have my apothem, now it's Mickey Mouse. Area equals 1/2 of apothem times perimeter. 16 times 5 is 80. So that's 40. So 40 times 11.01 will equal 440.4, bless you, units squared. Okay? So you must remember your sine, cosine, and tangent. If you don't, I suggest strongly for you to rewatch the videos on those. Okay? All right, guys. I'll take that as a yes. Hope you learned a lot. Have a great day, and thank you very much.